Okay, for this problem, I'm actually going to make use of a theorem that's in the notes, but I want to go ahead and state that theorem for you. So if I have a non-empty set of vectors S in a vector space V, if S is linearly independent and a vector V is outside of the span of that set, then if I take that set and join vector V with it, I still have a linearly independent set. And then the second part of that theorem says that if I have a vector in that set S and it's expressible as a linear combination of the other vectors in S, then I can actually remove that vector from S and that new set will still span the same space. So I'm going to make use of that theorem in this problem. And this problem, the first part of it is to show that these two second-degree polynomials, so we'll view this as being in P2, let's show that they are linearly independent. Well, the problem of showing that a set of two things is linearly independent, that's actually a very easy problem because the only way that it would be linearly dependent is if the vectors were constant multiples of each other. And it's pretty clear, hopefully it is to you, that there's no number I can multiply this polynomial by to get that polynomial. For example, if I multiplied this by 2, in order to match the constant, notice I would not get the coefficient of x squared to be correct. And then if I just said let's multiply it by 1 so that the coefficient of x squared matched, obviously the constant doesn't match. So in other words, P1 cannot be written as some constant times P2, right? And so this set then would have to be linearly independent. And of course, the more things you have, the more vectors you have in a set, the more difficult that becomes. Again, with only two things, it's very easy. But once I add in a third thing, then it's going to be a little bit more complicated. But here's where I'm going to use that theorem that I made note of at the top of this video. Show that if I take these two vectors and I adjoin this vector to that, that's still linearly independent. So remember what the theorem said. The theorem said, in fact, it's the first part of the theorem, if I have a linearly independent set, check, and I have a vector that is outside of the span of that, then when I join this vector with that set, which is what I have here, it's still linearly independent. So basically, I just need to show that there is no way that I can do a linear combination of these two and get that. And hopefully that is fairly obvious to you. Neither of these two things has an x cubed term in them. So there's no way that I can multiply these two by constants, add them together, and get x cubed from that. So P3 is not a linear combination of P1 and P2. So by theorem, since P1, the set P1, P2 is linearly independent, then that set with P3 joined to it, so, union that set, or in other words, P1, P2, P3 must also be linearly independent. Now, did you have to do this problem this way? No, of course you didn't. What you could have done was you could have done this in the same way we've done before. For example, I could write this as a column vector 1, 0, negative 1. This one is 2, 0, negative 1. Oh, wait a minute. So that's going to have to be 1, 0, negative 1, 0. I said earlier that I'm looking this in P2, which this is fine, but once I add this in, it needs to be at least in P3. So 1, 0, negative 1, 0, 2, 0, negative 1, 0, and 0, 0, 0, 1. And then just tried to show that that's linearly independent by looking at the augmented matrix for the homogeneous system. So you could have done the problem in that way. But making note of the theorem, this was a little bit easier way to do that. Hopefully that makes sense. If you have any questions, please let me know.